بسم الله الرحمن الرحيم والصلاة والسلام على رسوله الكريم. أبنائي وبناتي طلبة الإلكترونيات في قسم الهندسة الكهربائية، أسعد الله أوقاتكم بكل الخير. محاضرتنا اليوم التي سنقوم بتسجيلها هي محاضرة حول مقدمة على مادة الأوبريشنال أمبليفاير، تتعلق بثيوري of op-amp والليميتيشن للأوبريشنال أمبليفاير بشكل عام. خلينا إذا نبدأ هذه المحاضرة على النحو التالي. نقول بالله الاستعانة theory of operational amplifier. This is the circuit model of an operation or symbol of an operational amplifier. An operational amplifier is a DC amplifier that has two inputs and one output. Two inputs and one output. DC amplifier means that it operates from frequency equal 0. طبعا the upper frequency is limited by a certain cutoff frequency. هذه الفريكونسي راح ندرسها في وقت لاحق to represent what we called a limitation of the operational amplifier. نرجع الآن للإنبوتس للأوب أمب. لاحظوا إنه فيها عندنا two inputs، واحدة noted minus والثانية noted plus. Now the minus input, if the signal is applied on the V minus, the output will be inverted in phase with respect to the input. This means that the output is 180 degrees out of phase with respect to the input, and in this case, this input will be called an inverting input. If the input is applied on the positive input V plus, the output will not be inverted. The output will be in phase with respect to the input, and in this case, this is called a non-inverting input. Now, the output voltage, VO, equals to A, V plus minus V minus. A, V plus minus V minus. A represents the gain of the amplifier. A represents the gain of the amplifier. Note here that the operational amplifier is biased between plus VCC and minus VCC. It might be plus VCC and minus VEE. Generally, we take the two signals of the same value, plus VCC and minus VCC, to represent the maximum voltage that can be seen at the output. طبعا الاوتبوت عادة بتكون اقل شوي من VCC، يعني assume or suppose that VCC مثلا 15 volt, the output will be in the range of 13.6 volts plus and minus. Okay, now let's begin our study by what we call the ideal operational amplifier. The ideal operational amplifier. The ideal operational amplifier is characterized by the following. First, infinite voltage gain. This means that A is infinity. Second, infinite input resistance, Rn infinity. This means that the equivalent resistance between the two inputs, take this here, the equivalent resistance seen between the plus and minus inputs is equal to infinity. This means that there's no current will enter the amplifier through the generator. So Rn is infinity. And third, the output resistance is zero. So a zero output resistance. This is RO equal zero. RO is the resistance that be connected between the equivalent dependent source between controlled by the input and the output. هاي الريزيستنس اللي هون اللي هي RO. هذه RO for an ideal operational amplifier equals to zero. So the model of an op-amp ideal تقريبا will be like this. Here we have the two inputs V minus and V plus, open circuit between them. This is the dependent or the controlled voltage source representing the gain A V plus minus V minus to produce the output voltage with an output resistance on equals to 0. So this is the ideal model of operational and op amp with A infinity, with A infinity. Now, in order to produce an output proportional to the input, so finite output. finite output ليش؟ انه لاحظوا انه في الدائره هاي اللي هون اللي اعتبرناها بتمثل symbol للاوب امب when you take V plus minus V minus of any value, V plus minus V minus of any value, let's say V plus minus V minus equal to epsilon. This is epsilon of any value. Multiply by A, which is an infinite value. So the output will be infinity. The output will be infinity. Infinity, this means that the output will be equal either to plus VCC or minus VCC. The output will be equal to plus VCC or minus VCC because the infinite value means the maximum allowable voltage at the operational amplifier, which is plus or minus VCC. So if epsilon here is positive, so the output will be plus VCC. If epsilon is negative, the output is minus VCC. Or this means that if V plus is greater than V minus, the output will be plus VCC. If V minus is greater than V plus, the output will be minus VCC. So in order to get a finite output less than VCC and proportional to a certain input voltage VI, we have to use a negative feedback. A negative feedback, so a fraction of the output is fed back to the negative input. A fraction of the output will be fed back to the negative input. This fraction will be R1 divided by R1 plus RF VO. R1 divided by R1 plus RF VO. So this is the fraction of the output that will be fed back to the input. The input will be either VI connected to the minus input. This will be the inverting mode operation, or this input will be at the plus input with the feedback remark RF and R1 will be grounded. This is the non-inverting mode operation. So we have two modes of operation for this circuit: inverting mode of operation and non-inverting mode of operation. Let's begin our study by the inverting mode of operation. The circuit is like this. Here RF and R1 representing the feedback. The gain A, which is infinity. We study an ideal op-amp to produce the output voltage with respect to the input, means to calculate the gain of the circuit. Let's begin by using this node as the minus input. Here I have a current I1. Here I have a current I which must be 0 because the ideal op-amp, there is no current entering the amplifier. And here I have the current IF. So the I1 equals II plus IF. II is 0. So the VI minus V minus divided by R1, which is I1, equals V minus minus VO divided by RF, which is IF. So if we take the limit of VO divided by A as A tends to infinity, this will be the limit of V plus minus V minus, because VO equals A, V plus minus V minus divided by A, dividing by A, producing VO divided by A. So the limit as A tends to infinity will be 0. This limit will be 0. This means that V plus equals V minus or V minus equals V plus. And this relationship is valid as long as a feedback is connected between the output and the negative input. So always we have V plus equals V minus, or V minus equals V plus. So in this circuit, V plus equals 0. So V minus will be also 0, and it's called virtual ground. So V minus in this case is called the virtual ground. So replace 0 instead of V minus in this expression. This will give the voltage gain VO divided by VI equals minus RF divided by R1, minus RF divided by R1. So this value is negative, or this gain is negative. We said that this is an inverting mode. So we remarked the negative sign means the inversion of the output with respect to the input, the inversion of the output with respect to the input. So when the input is positive, the output is negative. When the input is negative, the output is positive. This is the first property. The second, this gain can be either plus, greater than 1, smaller than 1 in amplitude, or equal to 1 if RF equals R1, negative. And finally, it is independent of the op-amp. Remark that it is independent of A and RI and RO, etc. for the ideal operational amplifier. This is the first type of operation. Now, consider the non-inverting mode of operation. Non-inverting mode, this means that the input is at VI and R1 is grounded. So in this case, as there's no current in RC, the V plus will be equal to VI. The V plus equal to VI, and this is equal to V minus, equal to V minus. So here we have VI. Take the same node equation, I1 equals IF, because II equals 0. So 0 minus V minus divided by R1 equals V minus minus RF divided, V minus asset minus VO divided by RF equal to IF. So here also, we, as V minus equals V plus equal to VI, the expression VO by VI, which is the gain, will be equal to 1 plus RF divided by R1, or R1 plus RF divided by R1, divided by R1. So either 1 plus RF divided by R1, or R1 plus RF divided by R1. This is the voltage gain of a non-inverting mode amplifier. Remark that it is positive. Second, it is always greater than or equal to 1. The minimum value is 1. And it is independent of the amplifier. So this gain equals to 1 either when RF equals 0, or when R1 equals infinity. This circuit is called, as the gain equals 1, is called the buffer circuit. And it has certain number of applications. Here, so we studied the two types of operation, two modes of operation of an operational amplifier. Now, the ideal operational amplifier studied has certain number of limitations. So these limitations are, the most important of them are 3. The first one is the closed loop bandwidth, which represents the maximum frequency that can be operated in this circuit. The operational amplifier is a DC amplifier, so it operates from 0. There is a high cutoff frequency. There is a high value of frequency for which at which the operation can be get without distortion. Without distortion. Now, the difference between this cutoff frequency and the 0 for the minimum frequency is representing the bandwidth. So omega high, or F high minus F low, equals the bandwidth. F high is called F node here, which is the upper cutoff frequency. So the upper cutoff frequency is the bandwidth because the lower cutoff frequency is 0. So in this case, we have to determine this upper cutoff frequency F node. Now, the operational amplifier operates as a first order system. First order system, this means that since the frequency F node, which is the cutoff frequency, the slope of this amplitude of gain with respect to the frequency is minus 20 dB per decade if the gain is in linear scale and the frequency in log scale. So if we study or sketch this signal as log scale, this means here we have 20 log amplitude of A, and here we have 20 log frequency. So this slope will become equal to 1. And as you know, the slope is y2 minus y1 divided by x2 minus x1. So it is the, if we take this variation until a frequency called ft, at which the gain becomes equal to 1, and frequency called unity gain frequency. This unity gain frequency is a characteristic of the amplifier, and it is a part of the characteristic of the amplifier in its datasheet system. So here we have even the log of 1 minus log of f0 divided by log of ft minus log of f node equals minus 1. This is the slope of this straight line. So arranging this expression, we get f node equals ft divided by a. F node, the cutoff frequency, the upper cutoff frequency of the circuit, equal to ft divided by a. So f node multiplied by a equals to ft. Ft is constant for the specific operational amplifier. Ft is constant. So f node multiplied by a is the bandwidth multiplied by the gain, and we have the gain bandwidth product is constant. ولذلك الفريكونسي اف تي عاده is called the gain bandwidth product. Gain bandwidth product for an amplifier. So as ft is constant for the specific op amp, if we increase the gain, the frequency will decrease. If we increase the frequency, the gain will decrease in order to have a maximum product equal to ft. Sorry. This is an example for this circuit. What is the maximum frequency for an op amp if its ft equal 10 to 6 hertz and its gain must be 10? So 10 to 6 divided by 10 equals 10 to 5 hertz. This is the maximum frequency allowed for this circuit. Second example, if the amplifier must have a gain of 20 and its ft equal 10 to 6, so the maximum frequency that can operate without distortion will be 10 to 6 divided by 20, so 5, 10 to 4, 50 kilohertz, the maximum frequency for this operational amplifier. Now, if we want to operate at a gain higher than this one, so and we need a certain frequency of operation that higher than a certain value, so we can divide the operation into more than one op amp. Let's take this example, assuming the first 20k 5k as the feedback circuit, 50k and 10k for the second op amp. For the first one, remark that FO1 equal 10 to 6 divided by 4, which is 2.5 10 to 5 hertz or 0.25 megahertz. For the second, FO2 10 to 5 to 6 divided by 5, which is 0.2 megahertz. So we can increase using this system the operation up to a certain frequency in the range of 200 kilohertz or zero point 0.2 megahertz, which is greater than the value 5 10 to 4 or 50 kilohertz. So in general, in order to increase the bandwidth for a certain gain, we can divide this gain on more than one op-amp circuit. The product of the gain for each one will be the product of the total gain, and we have an operation with a higher frequency. This is the first limitation of the operational amplifier. Now, the second limitation is the slew rate. The slew rate S. The slew rate S is defined as the maximum rate of change of the output voltage of an amplifier. لاحظوا, the maximum rate of change of the output voltage. So first maximum, this means maximum. Rate of change is the delta V by delta T, and output, so delta VO by delta T maximum. Also S will be delta VO by delta T maximum or dVO by dt maximum. The output of an amplifier cannot be reached instantly as an input is applied due to the different capacitors in the amplifier model. If it will be increased exponentially like this, and we cannot have an instant variation like this to get the output. So the output will be increased exponentially until we get the maximum value. So it will be increased exponentially to reach the maximum voltage required by the gain and the signal of the amplifier. I will try to explain this using square signal. Assume this is the square signal. This is T over 2, and this is T. In this case, the output will increase exponentially to get the maximum. The maximum, assume we have a gain of G1, so the output must be G1 VI1. G1 VI1, this is VI. So must reach this value. So using due to slew rate, the output will vary exponentially. So we will get a certain output like this. We reach the maximum, and then it will decrease like this. So this is the signal for this case, a certain period or a certain frequency and certain gain, certain amplitude. Now, if we increase the gain to G2, so the output must become G2 VI1. In this case, due to slew rate, the output will increase in the same way. So like this until we reach this point. So we will not reach the maximum, and at this point the output will decrease again like this. So we cannot reach the maximum required for this new gain at the same frequency. So here we have a limitation on the gain. The maximum gain is this value. The maximum gain is this value multiplied by the input to produce this output, which is at the limit of operation. Now, if we increase the frequency, so decrease the period. Then the same variation, the same variation, this is the first one, first gain. We have the same variation, and we will not reach the required value. We will not reach the required value, and here we have a decrease like this. So أيضا هون we have a limitation on the frequency. Then due to slew rate, we have a limitation on the gain, and we have a limitation on the frequency. We have a limitation on the frequency. So if we take an output and signal sine wave, so the input signal will be VIM sine omega t. Using a gain G, the output will be G VIM sine omega t. Now, the slew rate is delta VO by delta T maximum. So it is omega G VIM cosine omega t maximum. Cosine omega t maximum equals to 1. So S, the slow rate, equal to omega g VIM. Omega g VIM. So a maximum allowable frequency will be the slow rate divided by g VIM, or a maximum allowable gain will be the slow rate divided by omega VIM. So in this case, if the slow rate is given, we can determine whether the signal will pass or will not pass due to slow rate. This is an example. Example, if the input Vi is composed of 3 components for this circuit, here we have 120 kilo ohm as a feedback resistance, 20 kilo ohm as R1. This is Vi and this is Vo. For this circuit, this amplifier, we give the slow rate equal to 0.1 volt per second. The components are Vi1 equals 1 volt sine 2 10 to 4 t. So omega 1 equals 2 10 to 4 radian per second, or 20 kilo radian per second. VIM equals 0.5 volt sine 3 10 to 4 t. Omega for this signal is 30 kilo radian per second. And the third component is 0.1 volt sine 5 10 to 10 t. So the frequency, the radian frequency of this signal is 500 kilo, or 0.5 mega radian per second. So it is required to determine whether these signals will pass or not through this amplifier. Mark that the gain for this circuit is 120 divided by 20 is 6 in absolute value. It is minus 6 in signed value. So find the components that will pass through the amplifier without distortion. If any will be distorted, so find a solution in order to pass them all without distortion. This means without modifying the amplifier. So the slow rate is constant. So we have to modify the gain, as we said before. Right. Let's begin by the first signal. For the first signal, we have 0.1 10 to 6, which is the slow rate, divided by the gain, which is 6, amplitude equals 1. So it is 1.667 10 to 4 radian per second. Radian per second. The frequency required is 2 10 to 4, and this signal maximum is 1.667. So this signal will not pass. The signal will not pass. Now, the second signal, 0.1 10 to 6 divided by 6 multiplied by 0.5 is 33.3 kilo radian per second. The signal is 30 kilo radian per second. This value is greater than the frequency given, so the signal will pass. The third 0.1 10 to 6 divided by 6 multiplied by 0.1, which is the amplitude, is 1.667 10 to 6 radian per second. The frequency required is 5 10 to 5 radian per second, and this signal will not pass. This signal also will not pass. So we have two components that will not pass. We need to determine the gain required for each signal, and then we will take the smaller one between them. We will take the smallest. So let's begin by first one. The G1 maximum must be less than or equal to 0.1 10 to 6 divided by 1, which is the amplitude, 2 to 4 to 10 to 4, which is the frequency required. This gain equal to 5. The second signal, the third one, 0.1 10 to 6 divided by 0.1 multiplied by 5 10 to 5 equal to 2. So we will take the smaller one between them, which is 2. So we will change the circuit to produce a gain of 2. If we need the gain of 6, so we have to use 3 stages of amplifier, or 4 stages for this amplifier, to produce the overall gain of 6. So the circuit will be modified like this. RF must be equal to twice R1. تمام. The third limitation for this circuit will be the offset voltage and current, DC offset voltage of current, and this is an output voltage at the amplifier with input voltage equals to 0. This output voltage or non-zero output voltage will be due to the mismatching of both inputs of the first stage of the amplifier. The first stage is a differential amplifier. If both transistors are not exactly identical, so a small value of current and voltage, IB and VBE, will be present at the input, and this current and voltage will be amplified hundreds of times to produce an output which is non-zero. So if the inputs are equal to 0, the output is not equal to 0. We have two things to study: the input bias current, which is the difference between IB of the first transistor, and IB of the second transistor, so IB1 and IB2. This is the model of the circuit. A certain current at the negative input and a certain current at the positive input, a certain current at the negative input and a certain current at the positive input, and this is the model of the circuit. So using source transformation, we will get such circuit: IB minus R1 as the voltage source, the RF R1, and IB plus RC with RC, and this is the circuit. So using superposition of the two inputs, VO1 will be minus RF divided by R1 multiplied by IB minus R1. And the second output, VO2, will be equal to 1 plus RF divided by R1 multiplied by IB plus RC. So simplifying this expression, we will get the expression V offset due to the input bias current equal to 1 plus RF divided by R1 RC IB plus minus RF IB minus RF IB minus. IB plus and IB minus are unknown values. So we try to reduce the effect of IB plus and B minus by taking an optimum value of RC equal to R1 parallel with RF. If we choose RC equal to R1 parallel with RF, so R1 plus RF, R1 RF divided by R1 plus RF, like this, the expression here will be reduced to V offset of IB equal to RF IB plus minus IB minus, IB plus minus IB minus. So this is the optimum value of offset voltage at the output due to the input offset bias current. So the value of IB plus minus IB minus is called IIO, called input offset current, and this value is present as a characteristics of the amplifier in the data sheet of the op-amp, so if RC equal to R optimum, the R1 parallel مع RF, so we can directly calculate the optimum value of offset voltage and current, وبنقدر نحتاج لهذه القيمة في الدراسات، وخاصة when we study a system with very low input. So now a second value is also present in the data sheet of the amplifier, which is called the input offset, the input bias current. So sorry, the input bias current IB is also a part of the data sheet. This input bias current is given by IB plus IB minus divided by 2. IB plus IB minus divided by 2. So in this case, using these two expressions for IIO and IB, we can get the values of IB plus and IB minus in two ways. If IB plus equal to IB minus, IB plus will be IB plus equal to IB plus 1/2 of IIO, and IB minus equal IB minus 1/2 of IIO. If IB plus is smaller than IB minus, IB plus will be IB minus 1/2 of IIO, and IB minus equal to IB plus 1/2 of IIO. So in general, for these circuits, we will study the two cases and be careful of the worst case. So we will study the worst case, and in this case, we have to be careful when we make a certain experiment or project also. Let's take this example. This is an operational amplifier with RF equal 100, R1 20, and RC equal to 30K. السؤال بيقول in this circuit the amplifier if IB equals 120 nanoampere and IIO equal to 40 nanoampere. Find the worst case output offset voltage. So the RC optimum equal to 20 parallel with 100, which is 16.67, which is not equal to RC. So RC is not the optimum. Now in this case, we have to use the general form of calculation, and we have to take the cases of IB plus greater than IB minus and vice versa. So if IB plus is greater than IB minus, IB plus will be 140 nanoampere and IB minus will be 100 nanoampere. And the gain 1 plus RF divided by R1 equal to 6. Using this expression, this general expression here, we will get the V offset due to IB equals 6 multiplied by 30, 10 to 3, multiplied by 140, 10 to minus 9, minus 110 to 3, which is RF, multiplied by 110 to minus 9, which is IB minus. This will get produce 15.2 millivolt. The second case, when IB plus is smaller than IB minus, so we get 4 millivolts. So remark that the worst case is 15.2 millivolt. The worst case is the 15.2 millivolt when IB plus is greater than IB minus. Now, the input offset voltage generally is always modeled at the positive input to produce the worst possibility. So VIO is modeled at the positive input. So the output offset voltage due to VIO will be 1 plus RF divided by R1 VIO. And using the previous example, VIO equal 2 millivolt, the V offset of VIO equal to 12 millivolt. So the worst case for both input bias current and input offset voltage, the offset voltage will be equal to 27.2 when both are positive or both are negative. Now, the best case is if one of them is negative, yani minus 15.2 and plus 12, or 15.2 and minus 12. In this case, the best case will be equal to 3.2 millivolt. So we studied here the 3 limitations of an operational amplifier, so which are the frequency limitation by the closed loop bandwidth, the slow rate limitation affecting the frequency and the gain, and the DC offset voltage due to the input bias current and the input voltage input offset voltage. Now, number C, a real op-amp when the amplifier is real. Real, this means that A and Rn or Rn are finite. A finite, Rn finite, one of them at least. Ro is not zero. These are the 3 characteristics of an ideal operational amplifier. So we will use the model of the circuit and calculate the voltage gain using the circuit analysis methods. Here is my amplifier. Let's take an example. 150 for RF, 25K for R1, and we give A equal 100, which is a finite value. كل ما كانت A أقل كل ما كان الفرق أكبر بالنتائج. Rn equals 100K, and remark that this 100K is comparable to the 150 and the 25K. So I cannot consider it as infinity. And let's take Ro equals 0 to simplify the calculation. This is the model of the amplifier. Here I have the Rn, the gain equal to A equal to 100. The controlled voltage source equal to A V plus minus V minus, and I will call V plus minus V minus equal to Vn. So this is AVn, and this point is called minus Vn. Using this node, so minus Vn minus Vi divided by 25, minus Vn minus 0 divided by 100, زائد minus Vn minus Vo divided 150K equal to 0. Multiply by 300, I will get the first equation, which is minus 17 Vn minus 12 Vi equal to 2 Vo. Now, at the second node, I have Vo equal to AVn. So replace Vn equal to Vo divided by A. I will get Vo divided by Vi equal to minus 553 instead of minus 6 if the amplifier were ideal. طبعا مثل ما قلت كل ما كانت الجين أقل أو كل ما كانت الار ان أقل كل ما كانت difference بين الايديال فاليو والاكشوال فاليو أكبر. Now, we can study also circuits with several operational amplifiers to produce any operation we need, to produce any necessary system, to produce any output, إلى آخره. We can analyze all circuits with operational amplifiers. Always we use superposition when I have inputs or several inputs, like this circuit. We have here an input Vi1 equal to 0.3 volt. This amplifier has 25 RF and 5K as R1. The second amplifier has 100K RF, and I have two inputs. The VO1 due to the first stage with R1 of the second stage equal to 50K. And here I have an RC equal to 20K and an second input VI2 equal to 2 volts. So in this case, I will calculate VO1, then VO2. لاحظوا VO1 equals minus 25 divided by 5 multiplied by 0.3. This is minus 1.5 volt. And VO, I have two inputs, so superposition. The first part will be minus 100 divided by 50 ضرب VO1 will produce 3 volt. The second, this is a non-inverting mode, 1 plus 100 divided by 50 يعني 3 multiplied by 2 will produce 6 volts. So the overall output will be the sum of these two values, 3 plus 6 equal to 9 volts. A second example here, when I have a voltage divider at the input. So don't forget that in order to get a non-inverting mode calculation, we need 1 plus RF divided by R1 multiplied by the V plus, because we took V plus equal to V minus. So it is V plus that the value required to the calculation. So here we need to calculate the value V plus before applying 1 plus RF divided by R1. So V plus equals to 5 divided by 15 plus 5 multiplied by 4. So 1 volt. Then here we have VO1 equals 1 plus 50 divided by 10 multiplied by 1. So it is 6 volts. Now, here I have 6 volts. I have another input with 1 volt. So superposition, minus 40 divided by 20 multiplied by 1 multiplied by 6. So إذا عندي هون 2 في 6 equal minus 12. And the second input, 1 plus 40 divided by 20, which is 3, multiplied by 1 will produce plus 3 volts. So the overall output will be minus 12 plus 3 equal to minus 9 volt. Here I present for you certain study of the theory of operational amplifier. I hope that it is simple for you and you can understand it without any problem. If you have any questions, you can email me with your suggestion or your questions, or send it to me by WhatsApp. Thank you for everything, and we will see you in the next time. Wassalamu alaikum wa rahmatullahi wa barakatuh.